So in the second part of chapter 2, we're going to pick up where we left off. Just finished up descriptive research, and now we're going to go into correlational research. So correlational research is about measuring the relationships among variables. Okay, so the most straightforward correlational research has two variables. So you measure one variable, such as people's birth order. Then you measure a second variable, such as a personality trait, and you determine, you run it through stats, SPSS or whatever you're using. I think R is the new one. And you determine whether X and Y are related. It's important to note that when you're doing correlational research, you are just measuring the variables as they are. You're not manipulating anything. You're just trying to see if there is a relationship between the two. So this is what the data looks like when you plot it. Okay. So when the data is going, say height and weight on that far left one, when it's going on an upward trajectory like that, that is called a positive correlation, right? So as height goes up, weight goes up. A negative correlation would be measuring hours of sleep and tiredness, right? So as hours of sleep increase, tiredness decreases. I should have said that the other way around, but it's a negative correlation, right? And then shoe size and hours of sleep. Obviously, there should be no relationship there. And that's what a scatter plot looks like when there is no relationship, just sort of random all over the plot. So it's important to note that correlations can occur amongst random variables. Okay, this one here shows the number of people who died by becoming tangled in their bed sheets. Okay, so on the left you can see that as the consumption of cheese increased, okay, so did the instances of getting tangled in bed sheets. So there you can see a positive correlation between the two. Meaningless, really, but it does occur. So they're just things that go together. Doesn't necessarily mean that there's a valid reason for it doing so. So with correlation, you can have bidirectionality and spurious association. Okay, so for bidirectionality, you can have a two-way causality. You can have X causes Y or Y causes X associated with, right? Or you can have a spurious association, which is not genuine, and there is a third variable problem. Okay, so let's go back up to A there. So A, social relationships and happiness are correlated. So better relationships equals better happiness. Those two go together. Bidirectional problem. So does X cause Y? Better social relationships cause greater happiness, or does greater happiness cause better social relationships? Okay. And the third variable problem, there may be no causal relationship between X and Y at all. Okay, there could be something else. So you have better social relationships, greater happiness, but there's actually a third variable that's involved. So how do you measure the strength of a relationship? Okay, that's called the correlation coefficient. So when you run the stats, and the math is a little bit complicated to get into here, that's something you would do in second year in your stats class. But the result is going to give you a correlation coefficient. And it ranges from -1 to 1. And whether it's a negative or a positive shows you the direction of the relationship. So if you were to measure two things together, say happiness and social relationships, and it came back as a 0, that's 0. I mean, it never comes as an exact 0. That's a 0 correlation between the two. If you were to come with a +5, that's a positive correlation. And if you were to have a -5, that's a negative correlation. So there's two parts that are important to a correlation coefficient. One is whether it's a negative or a positive. And then the second is the number. What does a 5 mean? Is that a lot? Is it not? Where do we say that, oh yes, there is a relationship? Is that at 0.2, 0.3, 0.4? And that's where we have this chart. So let's say that you put you ran the stats and you ended up with a 0.3. So what you would report in your findings is that you found an R equals 0.3, which is a weak relationship. Now, if you did your research and the stats came back and you had a 0.75, oh, well, now you're really excited because you found a strong relationship. Okay, so you use this chart in your description of your results to indicate the strength of the relationship. Again here, positive correlation. As height increases, so does weight. That's got a R equals 0.4, which is slightly more than the middle number there. And then a negative correlation, which means the variables are changing in opposite directions. So a negative correlation would be R equals -6, and that would be a rather strong negative correlation. Here's some more examples of scatter plots. That's what the visual is called. Yeah, so variable y, grade point average, hours of studying per week, and as you expect, it would be a positive correlation. 0 correlation, again, grade point average and number of apples consumed per week, none. And then grade point average and hours of TV watch would be a negative correlation. So advantages of correlation study, they show the strength of relationships that are present, and they can be used to make predictions about variables, right? So some research has shown that people's math and English scores are positively correlated to success in education, right? They identify real-world associations, so they say. Disadvantage, you cannot assume a cause-effect relationship. Okay, you can't prove. You could intuitively understand that the number of hours spent studying increases has a positive relationship with your grades, but it's not a cause effect. You haven't proven that here. To do that, you need to do an experiment, right? Relationships may be due to a third unmeasurable variable. There could be something that you're not considering that's actually causing the relationship. Okay, so the third, experiments. 3 essential characteristics. Manipulate one of the variables. You measure whether this variable produces change in another variable, and you try to control for factors that might influence the results. So just like the light coming in on the plant, you have everything be the same. You have the size of the plant, the age of the plant, the type of the plant, height, density. Try to have it exactly the same as the other plant, and the only thing that changes is whether it's getting sunlight or green light. And that way you can reasonably assume that any change would be due to that one factor. Experimental group receives the treatment, control group does not. Key thing to experiments is random assignment. If you do not have random assignment, it's one of the rules. Remember I said there's lots of rules to data analysis? It is one of the fundamental rules of data analysis. You have to have random assignment. There's an actual test you can do on your data to see if the data is random, if it's a normal distribution. If you do not have random assignment, you cannot do a lot of statistics. You'd have to do descriptive. Two basic ways to design an experiment. There are many ways. This is just in its simplest form. Between groups. So a between groups design means that each group has its own intervention and you measure them at the end. And since people are randomly assigned to group 1, 2, or 3, then you're going to assume that the differences are due to the treatment. Okay? Within groups, participants participate in all of the conditions or in one condition over time. Okay? So you'll have one sample and they'll undergo the treatment condition 1. Usually they'll be tested there. And then they'll all do condition 2 and they'll all do 3 being tested each time. Okay? The variation of that is the repeated measures, which means that you're going to test the group, they'll have a treatment, and then maybe 3 months later have another treatment, and 3 months later have another test, and then 3 months later and have another test. So let's say that a group of students underwent some sort of study training for preparation for exams for school that was supposed to decrease anxiety. Okay, so they all go through this training and then you measure them. Say after 6 weeks, you measure them and see how they're doing. Now, the reason you'd want to possibly do it in another 6 weeks or in 3 months is that it's great that it lasts 6 weeks, but is that it? Like, is this a sustainable change, this learning that they've done? So you're going to want to check it in 6 months, and you're going to want to check it, say, in 12 months and see how long the effect lasts. So that would be a repeated measures design. There's time point 1, time point 2, time point 3. This one's trickier to do, of course, because you have attrition. You have, maybe in the first group, you have everybody. Second group, a little less enthusiastic about participating. By the time you get to the third group, which is 6 months later or 12 months later, people have moved. People just don't answer. Some move on in life or out of. There's lots of reasons, so it's difficult to do. It's difficult to try to get enough participants in the later tests. A two-way ANOVA. This is when you have two independent variables. Okay. So let's say that you're measuring the effects of cell phone use and traffic density on driving performance. Okay. So the two independent variables are cell phone use and traffic density, and the dependent variable, the things you're measuring, is the driving performance. The reason you're doing both, if you were just doing cell phone use and driving performance, you're only going to find out cell phone use and driving performance. When you're doing two like this, what you're trying to discover, what this allows you to do, is find the interaction effect of cell phone use and traffic. When you put them together, they may have an increased effect, the combination of the two, right? So you can see there on the chart, you've got drive and low traffic density, and then drive and high traffic density. And you've got your two bars there. Now, when you combine that with So now you've got low plus cell phone and high plus cell phone. And you can see there that the purples, high plus cell phone, it appears that there is an interaction effect, because look at the jump in the purple under the high traffic density when you're combining it with the cell phone use. So again, when you're doing a two-way ANOVA, when you're doing any sort of, or there's MANOVA when you have more, but anyways, when you have two independent variables, you're looking for not just measuring the two pieces, not just measuring cell phones or measuring traffic, you're looking if there's an interaction of the two. Okay, this is my YouTube video that will not play the way I have this set right now. So if you will hold on 1 second, I shall be right back.